Hello guys, welcome to my dimmer series episode 2. We will try to understand the logic behind dimming. So, how's your light or a fan dims? We are talking here particularly about AC loads, not DC loads, because generally the loads that we see in our day-to-day life are AC loads. uh, we do have AC loads such as your LED lights, your monitors, your printers, your laptop sometimes. But in this series, we are particularly focused about AC loads right now. So that's why we are just talking about DC. So we will be discussing the methods of dimming the AC load. First being the phase control or zero crossing control. I've seen many authors use it with either of the name, but both the methods are same. Basically, we are trying to observe the zero crossing point of a sine wave, and based on which we inject a delay and we give it to the load. Second is a capacitor based dimming, so it's basically a peak to peak or a voltage based control. Third one is soft dimming, that is also a voltage based control. Yeah, so uh, phase control and zero crossing control method. In this method, what we are seeing is there are two diagrams. Why is it control, phase control, and zero crossing control is because of this sine wave. What is happening here is we inject some delay in the sine wave which is given to the load. Since this delay causes the net voltage which is appearing uh, on the load, which tends to dim the light or a fan. Okay, so what is happening, how it is being done, how we generate the delay. So once the energy start flowing, your both the dike and trike is not conducting. Okay, the moment it charges the capacitor through this resistor and this pot. Okay, so let's say it charges to a voltage level of 30 volt. Okay, and this diac has a reverse breakdown voltage of 30 volt. So what is happening is this diac starts conducting. Once this diode start conducting, this trike start conducting. So how is it happening is this capacitor get discharged through this cycle. Okay, and the energy which is flowing from the load is from AC supply to the load to the trike and back to the AC supply. Okay, so this 32 voltage has produced some delay. Okay, so that delay is being given to the load. Okay, and what is happening in the negative half cycle? In the negative half cycle, the same is happening. It it charges with the reverse polarity. The other set of diac will conduct, and other set of triac will conduct, and that's how the delay in the second half is seen in the load. Okay, so now you have seen this is a non-isolated approach. What do you mean by non-isolated approach? Non-isolated approach is where your AC, where is your high voltage and low voltage is not isolated, means they are electrically connected in the system. Let's come to the right hand side, which is your isolated system. Okay, so there you have seen two isolators. One is optocoupler and another is optoisolator. Okay, so this optocoupler H11AA1 is used to detect the zero crossing. Whenever the sine wave passes, whether it is rising or falling, rising, I say rising and falling, it detects both the points. Okay, it detects both the points. So once it is rising, it will give you uh, one pulse. At the falling edge, it will give you another pulse. Okay, so these two pulse will get recorded in the MCU. Okay, so you can use any MCU, any 8-bit or 16-bit or any MCU, I would say. Okay, the moment your controller detects this pulse of 10 millisecond or 20 millisecond, based on which we can put a delay through this pot. Okay, we can put a delay through this pot, and we can uh, 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 we can control the current which is going through this opto isolator. Okay, uh, so this will create the delay. Understood? The moment you have detected the zero crossing. Okay, your pot has some value. That pot value uh, will result in some form of current in this opto led, I would say. Okay, and this will in turn uh, give the turn on my track uh, after some time. Okay, this will create the delay. So this is the delay which is being created through this, whether it is positive rising edge or a falling edge. Okay. Secondly would be your capacitor based dimming, or I would say peak to peak dimming, or I would say resistive based dimming. All are same. So what is happening is your resistors are connected in sorry, your capacitors are connected in some particular fashion, and there is a knob. Okay, so as you can see, the load is connected in the series, and you have to switch between different capacitors. What is happening is, when you put the capacitor in series with the with any source, whether it if it uh, whether it is AC source or a DC source, the capacitor is bound to have some voltage across it. So that is the voltage we need to drop across the capacitor, so that ultimately my load gets the less voltage. Okay, it is as simple as that. Okay, and why 3? Because we have to dim the light or any AC application or any AC load in three different dimming patterns or something like that. Okay, so another is soft dimming. So this is very interesting. This is the reason why I made this entire dimmer series, and I would be covering particularly. So what is happening is, your load is connected in series with the source, and there is a device, there is a switch. Okay, switch has its own control mechanism. So we are controlling the voltage. Okay, but we are this is not a I would say your zero crossing or a simple resistive or a capacitive control. This approach is way different, way unique. That's why I have covered it differently. Most, you won't find much of a content on this particular approach. So I will be covering this and the challenges behind it. So guys, that's my episode number 2 in the dimmer series. I hope you all like it. We will be covering it in detail. uh, Thank you for your patience. Peace.